Okay, so today we'll be starting with a new topic called statics and dynamics. Right? So the statics and dynamics, actually many people feel that actually this is one of the difficult subject, but in reality it's not. So this is actually one of the very easy subject in fact, right? The only thing is actually you have to understand certain fundamentals from the physics. So that is the only thing that you have to be aware. And rest of the thing is actually only the analysis part. So the concept actually needs to be clear. So the tough part is you have to learn new concepts. Right? And other than this, actually, this is analysis is easier, not that difficult. Right? Okay. Now, based on this understanding, actually, we will start with this particular topic. So, we'll be answering some certain questions like what is the syllabus? And the second one is what is the weightage? The next one is what are the books to follow? What are the books to follow? And the fourth one is what are the important areas? Focus. And the fifth one is approximate number of hours. Approximate number of hours. And any other question you wanted me to answer? Hope I have covered all. So tell me if at all anything I have to add it. Right? Now, in this particular topic, so there are two different parts which are actually completely drastically different. That is the statics and the dynamics. But why it was listed under the same category is here, whenever there is a force, and that force actually can have two different types of effects. One is force can move the particle from one location to another location. So that study is called as the dynamics, right? And if there is a force and if there is a counter force as well, in that case, there are two different forces equally balanced to each other. Forces are still acting, but there is no movement in that. In that case, the analysis we call this as the statics. So in both of these cases, we can conclude as a single topic, force and its effects. The same topic can even be extended to other categories like fluid dynamics also, where the force actually, if it is acting on the movable media, it's not like a single medium, wherein actually a single solid block versus the distributed medium where the force is acted on each and every individual particle of that particular mass, then the analysis is actually a bit different, but that also comes under the category of the dynamics itself. So that's actually we call that as the fluid dynamics. So there is actually one more topic, actually mechanics we will be studying. So mechanics is also actually a kind of the statics and dynamics related topic only. But the only thing is actually when there are multiple particles are moving with different velocities in different directions, then the analysis actually we are going to analyze with the help of that kinematics or the mechanics part, right? So these are all the related topics to each other. So finally, if you notice, the fundamental component in all the four topics, the statics, the dynamics, the fluid dynamics, and the kinematics or the mechanics, in every topic, force and its effects. That's it. Got it? Now, let us see in this particular topic. So there are, what is the syllabus of this? Let me go through the syllabus first. So this topic actually, it is the fifth topic of paper 1. It comes under section B of paper 1. And so this is actually starting with the syllabus rectilinear motion on the simple harmonic motion. Both are actually one and the same. So rectilinear motion meaning a particle, right? So it has a link with the fluid dynamics, right? As I said earlier, the fundamental component is actually force and its effects, but the way we analyze the fluid dynamics is completely different than what we are going to study here. The point is that actually a single particle analysis versus infinite particles together moving is completely different. So the system of particles what we are going to study in physics is more or less related to the fluid dynamics, right? So the analysis is completely different, but essentially the effects are actually exactly same like what we see it here. Now rectilinear motion is nothing but the particle whenever it is moving, usually we can think of what kind of analysis we do it. What kind of analysis? If you suppose actually, if I am saying a particle actually is moving from one location to another location. Now in that case actually, what are you expecting from that, right? So a particle, if it is moving, we can say that actually one-dimensional, two-dimensional, and three-dimensional motion, right? One-dimensional motion, three-dimensional motion, and two-dimensional and three-dimensional. So we have it in our syllabus actually, we will be studying only these two, that is one-dimensional and two-dimensional. And this one-dimensional actually we call this as the rectilinear motion. And this actually we call this as the planar motion. Right? We don't study this 3D motion actually, we don't study it in case of dynamics. And the analysis actually for the force and its effects actually in case of static, that is, suppose if there is a block of mass, there is a force that is acting here, there is a force that is acting here. If these two are balanced out, then actually there is a force acting, but still it is balanced, hence there is no movement, and this kind of analysis we study as the statics. So this is the statics. And there is a block of mass here, if there is a force that is acting on this, then actually this is going to be moving, F equal to ma, right? F equal to ma. And this kind of analysis what we study is the dynamics, right? So statics and dynamics actually we'll be studying it together here, and one-dimensional and two-dimensional only is part of our syllabus. So we don't study this three-dimensional motion. But actually in vector analysis, if you notice, we have studied even the three-dimensional motion also in the vector analysis, that is the Serret and Frenet formulae. There actually the curvature and torsion values we have calculated with the 3D motion. But here we limit our discussion to only these two because that is the part of our syllabus, right? Now rectilinear motion, meaning why this is complicated then? Because actually if it is a one-dimensional motion, two-dimensional motion, and we have studied at intermediate level itself, wherein actually there is a particle moving in a straight line. Like if I throw this pen like this, it goes in a straight line upwards and it comes back in a straight line downwards. Now this kind of analysis that we have studied at +2 standard itself, right? And the planar motion also, the projectile motion we have studied at +2 standard also. But here actually we are generalizing the discussion to more different ways. In the sense actually we don't study the polar motion or actually the polar kind of motion wherein actually the particle is moving radially outward. That is, the coordinate system is going to be changed, but still it is a one-dimensional motion. So moving only radially or moving only in the transverse direction or actually moving only in a straight line x-axis or actually moving straight line y-axis, like this actually we are going to divide this analysis into different categories, but still it is a single dimensional motion, right? So that is the one-dimensional motion. In case of two-dimensional motion, actually the motion of the particle when it is moving in a planar, that is on the xy plane, actually we move it, like in the case of a circular motion, or actually in the case of a projectile motion, we will be studying the planar motion. And other planar motion is like actually so that is the planet rotating in a elliptical orbit, that is the planar motion. So that is also called as the inverse square law. We are going to analyze that, and but everything is related to one-dimensional and two-dimensional analysis, right? So now actually, so this is the rectilinear motion and the simple harmonic motion are one and the same, because rectilinear motion meaning moving in a straight line, but simple harmonic motion moving in a straight line, 2 and 4 motion. So this is actually this way actually it is moving and coming back, but it is still the straight line itself. So that is what we call as the simple harmonic motion. And motion in a plane, so this is the planar motion, and the projectiles and constrained motion. So constrained motion meaning, suppose actually if a particle is rotated by tying up with a thread like this, like actually if you rotate it like this, then actually it is constrained to move in one specific direction, or actually it is constrained to move in a circular fashion only. So there is a constraint that is going to be associated there. So such kind of analysis also we do it. Suppose actually inside the big bowl, then actually if you throw a ball on the periphery of the bowl inside, then actually it is trying to rotate in a circular fashion like this. So such kind of motion actually you are restricting the particle to move in one specific direction only, or actually you are restricting to move in one specific fashion only. So that actually we are going to study in case of constrained motion. And work and energy, right? So work and energy, so that is actually both in statics and dynamics also we study this work and energy. That is, if a particle actually, if it is there like this, then at this particular height it is having certain amount of potential energy. And if I leave it, then actually it is moving with certain amount of velocity. Hence, actually it is going to be associated with certain amount of kinetic energy. So energy and how actually it is going to get the energy. If you do the work on this, supposedly if I lift the pen from the ground to this height, then I am doing the work. So as I am doing the work, the same amount of the work actually is going to be stored as part of the energy in this particular particle. Now that actually we are going to study as part of this work and energy and conservation of energy. So that is, energy can never be created nor destroyed. How mathematically actually we can prove that. And this is the Kepler's laws and orbits under central forces. So both are actually together. It's a single topic, that is the planetary motion. Planetary motion actually we'll be studying, right? So Kepler's laws and planetary motion. So orbits under central forces. And what is Kepler's laws is, there are three different Kepler's laws we study it. Every particle or every planet actually will rotate in a elliptical orbit. So this is an elliptical orbit, and that too in a planar shape. That is actually elliptical orbit actually. So one secular planet rotates in an elliptical orbit like this. Forever it will try to rotate only on the same ellipse, but it won't move like it. Once it goes like this, and then again actually it goes like this, again actually it goes like this. It won't do that. So that is, once if it assumes a single path, then that elliptical path throughout the life actually it follows. So that actually we will prove in case of Kepler's law. That is the first Kepler's law. And the second one is, the sectorial area is maintained constant, meaning the rate of change of area, that is with respect to the focus of the ellipse and the line joining from the ellipse to the planet, and that line actually it drives in such a manner that it covers equal sectorial areas in equal intervals of time. So that is the second law we are studying in the Kepler's laws. We prove that mathematically. And the third law is actually T square by R cube is going to be constant, where T is the period of rotation and R is the radial length. So the T square by R cube actually we are going to do it. So at +2 standard actually we study these just as the rules. And sectorial area is constant, rate of sectorial area is a constant, rotates in a planetary path, and T square by R cube is constant. These three actually we call as the Kepler's laws, and we don't know how to derive those formulas. But now we will be deriving those formulas with the vector analysis. So that is actually we are going to study it. And there is something called the central orbits. So what is the central orbits is, and this is one of the most important areas of focus for UPSC, because the questions especially comes from this central orbits only. So this Kepler's laws and the central orbits is actually one of the very, very important topic. And what is a central force is, if the line of action of the force is passing through a single point, then that is called as a central force. Let me explain again. See this, suppose, let us say you take this elliptical path, then actually sun is located at this particular point. Now, if the planet is located here, so the planet is attracted towards the sun. If the planet is located here, it is attracted towards the sun. If it is located here, it is attracted towards the sun. Now, if you notice, all these three lines are passing through a single point. So, these are actually passing through a single point. And if, so this is the line of action of the force. So, the line of action of the force is passing through a single point, hence this is called as a central force. So, this is what we call as the central force. If the line of action of the force passing through a single point, right, then that is called as a central force. So even the Kepler's laws also derived based on this concept of central force. And it has actually one more important aspect, that is, if the particle is moving in the central force, meaning the force is only in this particular direction, there is no transverse force. So as there is no transverse force, the force is always towards the center. Now in that case, actually the path is always in orbit. This we prove it mathematically. So if this is the case, the path is always, it is a planar shape, right? So that is, this is the path. So it has to be a plane, that we prove it. Got it? And this is what we call as the central force, and this we will be studying to a greater level. And then equilibrium of a, so that is the syllabus what we are going to study as part of dynamics. So that is the syllabus: rectilinear motion, simple harmonic motion, motion in a plane, projectiles, constrained motion, work and energy, conservation of energy, Kepler's laws, and orbits under central forces. So this is actually very simple and short syllabus and very easy to understand, and you should be able to solve all the problems related to that. Got it? And the next one is actually the statics part. So statics part, actually this is a bit more syllabus. There is equilibrium of a system of particles, and work and potential energy, friction, common catenary, principle of virtual work, stability of equilibrium, equilibrium of forces in 3D. So this is the complete syllabus what we are going to study as part of this statics. So what is the equilibrium of system of particles is, suppose if there is a single body, like, so if I take a solid body, let us say this pen, if I take it, if I apply a force here, then actually if I apply a force here, if equal forces are applied on either side, so it is going to be under stable equilibrium condition. So this is the equilibrium. But actually equilibrium of system of particles, meaning suppose actually this body itself actually is having infinite number of particles, or else actually you take two different particles. Suppose actually if there is one pen like this and there is finger like this, now actually these two are actually balanced and actually are staying here. Now there is a force that is applied by this finger, and there is a weight of this particular pen that is applied on my finger, and here also there is one support where there is a force acting on this. All these particles actually you can treat as independent particles, and this system actually, if it is under equilibrium condition, then how the force balance equations are going to be written. Based on that, actually whether we can conclude whether the stability, so whether this system is under equilibrium or not. Equilibrium by definition, when there are multiple forces are acting, but still there is no movement of these particles, then in that case we call that as a equilibrium. Now what are all the different conditions that we can check, so that actually when there are multiple forces that are acting, then actually whether those are going to be equilibrium or not. Now the problem is, in most of the cases what happens is, we will be studying only the planar forces, meaning assuming that all the forces are acting in a plane, then finding out the equilibrium is very easy. But when there are forces that are in 3D, then actually the complication actually is going to be a bit more to assure the equilibrium of the forces. That's why actually there is one more topic at the end, that is the equilibrium of forces in a 3-dimensional, right? So this actually we are going to study depending upon the type of beams that are going to be present in the forces. So all those things actually we'll be analyzing in case of 3D. And then actually, so equilibrium of system of work and potential energy, and there is actually something called the principle of virtual work. So what is the principle of virtual work is, if you give a virtual displacement for a system which is under stable condition or which is under equilibrium condition, and then actually the work done is going to be zero, because actually it will bring back to the same original system. That is, suppose actually assume let us say these are two different forces that are acting, and if you give a little bit of displacement, then again actually it will come back to the original position. So this is called as the stable equilibrium. Now in this case actually, if you do a little bit of work meaning if you move like this, you are doing an external work, then automatically it gives back that amount of the work. Now the effective work done is going to be zero in this particular equilibrium condition. So this work we call this as the virtual work, and based on that actually we will be able to identify some of the unknown forces involved in that particular system. So that actually we are going to study as part of this principle of virtual work. And potential energy and the work actually, so these concepts we will use in assuring whether the equilibrium is going to be stable or not. I'll give one more example. What is the stability of equilibrium is? See this, suppose actually assume that there is a shape like this, then actually there is a pin or a nail actually that is there attached to the wall. So this is the shape and this is actually the nail that is attached to the wall. Then actually it is under equilibrium condition, because actually this body is staying on the wall. So hence actually this is going to be stable. Now I'll give you one more system. Now there is the same shape is there, but the nail is located at this particular point. Now if I give a little displacement to this, will it come back or actually it goes away? It will come back, right? Definitely. And now in this case, I give actually a little bit of displacement in this. Now will it come back to the original position or it goes away? It goes away, right? Obviously, right? Now initially both are actually under balanced condition. That is because actually assume that actually the balanced weight is going to be there. Now in this case actually it is exactly balanced. Now it is under equilibrium condition, because actually this force or the weight of this particular body is balanced by this particular nail. Even here also it is the same case. But the problem is, if you give a little bit of displacement, then the problem comes. Otherwise actually it will be under equilibrium condition. So this condition is called as the unstable equilibrium. It is under equilibrium now, but if you give you a little bit of displacement, it is unstable. Here it is under equilibrium now, but if you give a little bit of displacement, again actually it is bringing back to the same original condition. Then actually this is called as a stable equilibrium, and this is the unstable equilibrium. And for this stable and unstable equilibrium, to find out, there are different techniques that we use it. That is, there is one concept, that is the work function concept, and another is the potential energy concept, and there is actually one more concept is there. So all those things we will be studying as part of this work and energy. So the stability of equilibrium is going to be assured based on this work energy. Got it? And the next one is the friction and the common catenary. So friction is a very basic concept. So whenever we apply a force, so this suppose actually if we are moving, then actually our legs are actually subjected to the friction, because actually it is under the ground. Now, whenever we talk about the forces, right, there are only two different kind of forces actually we will be talking about. What are those kind of forces? Can anybody guess what are those two kind of forces we talk about? Translation, centripetal, but these are actually all are actually same kind of forces only. But we talk about so two different forces. One is the conservative forces, and the second one is dissipative forces. Right? And in case of conservative forces, actually energy will be stored. But here, in case of dissipative forces, energy will be dissipated. Right? Will be dissipated. These are the two different kinds of forces actually we'll be talking about in our day-to-day life. So the only dissipative force we talk about is the friction. Right? Let me tell you what it is. Suppose actually I'm taking this particular pen, then actually I'm going to the other room and I'm keeping the pen over there. And again, actually I brought back the same pen to this particular same place. Now that means actually I'm here now and this is the other room. Then actually I have taken this pen to this location. Then I have brought back to the same position. Now what is the amount of work done? What is the work done in this particular case? I brought back to the same original position itself. In this case, actually the displacement is 0. Then what is the work done? But actually, is it justifiable? I'm walking from here to there, and again, actually, I'm coming back to the same position, right? So, are you saying that I have not done any work? Not justified, right? So, in reality, we are doing the work. I'll give you one more example. Suppose actually this pen, right, with my force, actually, I am bringing to this particular location. Then actually, this pen is always ready to bring back to the same original place. So because actually if I give you a chance, then actually it is trying to push my hand downward so that actually it is assuming the original position itself. Now actually while going up, actually I am doing the work. While coming down, I am not doing the work. In fact, this pen is doing the work on me. Yes or no? Right? Right? This kind of work, we call this as the conservative work. So this is actually conservative. So gravitational force is a conservative force, because actually while going up I am doing the work, and while going down actually the gravitation is doing the work on me. So the balance is going to be there. Now in this case actually the effective work done is 0, because actually it is going to this height and it is coming back to the same position. In this case the work done is going to be 0, because whatever the work I give to this particular pen, it is giving back to me. So essentially the work done is going to be 0. And this is possible only in the case of the conservative forces. And in case of non-conservative forces, work done is not 0, because while going this side, I am doing certain amount of work. While coming back, I am doing certain amount of work. And essentially, I am doing 2 times of the work. And this is a valid justification, because the work involved in this case is a dissipative work, or the energy is getting dissipated, because actually while walking from here to there, I am dissipating my energy. I am spending my energy completely while moving from this location to other location, right? So that work actually is going to be considered in case of the frictional force if it is involved, because while moving from here to there, I am subjected to a certain amount of friction by the ground, and this is a dissipative force. Got it? So that is the difference between the conservative forces and the frictional forces. And there are different kinds of frictions actually we talked about. One is actually, so that is the static friction and the dynamic friction. What is the static friction is, suppose if a body, so let us say if you take the car and then we try to push the car. Now initially the force I am applying on the car is not sufficient enough to move the car initially. And then actually eventually I'll keep on increase my force. That is, suppose actually, so This is how it is. Now this is the frictional force offered by the car, and this is the force actually what I am putting on this particular car. Then actually, if I increase my force, the frictional force is going to be increased, right? Or else actually, if I take the frictional force here and the force whatever I am applying, actually if I take it on the x-axis, then if I keep on increase the force, the frictional force also keeps on increases, and at certain level, the car starts moving. So if I apply 0 newtons, it won't move. If I apply 1 Newton, it won't move. If I apply 10 newtons, then also it won't move. If I apply 100 newtons, then actually it starts moving, right? So that time actually the initial friction that is going to be offered is keep on increasing with my force, and at one stage actually it starts moving. Then the frictional force actually suddenly it will be reduced to certain amount, and then actually the same amount is going to be maintained constant. So this is the highest friction actually it is going to be offering on me to move the car, and this is what we call as the static friction. So this height is going to be the static friction, and once actually the car starts moving, then actually it is easy for us to move, right? That you can feel manually, right? So once the car starts moving, you feel actually a bit relaxed to move. So that force actually is not required because the friction offered is less. That's why actually the friction is getting reduced a bit when it is moved. Then that amount of the friction is going to be maintained, and this is called as the kinetic friction. So this is the kinetic friction or dynamic friction. Right? So this concept actually we'll be studying, and this force, suppose actually if you are applying the same amount of the force, then actually this force is an extra, because earlier actually it used to offer this amount of friction, now it is offering only this amount of friction. There is a gap between these two. This will be used to accelerate the car based on the mass of the car, and it will give a certain amount of acceleration. Then actually car starts moving, so it keeps on actually raises its velocity if you apply the same amount of the force. Got it? So this is what actually we are going to study as part of this particular friction. And then actually and common catenary. So common catenary nowadays actually what we see on the outside, that is when there are two different electric poles are there are wires that are hanging between these two different poles. Then what is the shape of that particular wire? And that actually is what we call as the common catenary. And depending upon the weight and depending upon the position where it is going to be hanged out, that actually we are going to calculate the equation and the shape of the equation and the location where you wanted an interested point, like where it is subjected with the heavy weight, and all those things we are going to calculate as part of this common catenary. Got it? And then actually principle of virtual work I have already explained, stability of equilibrium I have already explained, and 3D forces also I have explained. So these are all the things actually what we are going to study as part of this one. Got it? Any questions? Right? And the weightage of this particular topic is, so this is comes under the paper 1, 5th topic, section B, and this is actually in the 2019 it was given a weightage of 70 marks, and 2018 actually we have got a weightage of is very less, 22 marks. I think maybe something might wrong here. Right? So dynamics and statics usually 60 to 70 marks we can assume. 60 to 70 marks minimum, that you have to keep it in mind. So and then so this is actually 75 marks in 2016, and in 2015 we have got around 84 marks. But in and around actually nowadays actually you get an average score of 70 marks for statics and dynamics. So that you can assume 70. Usually that is the weightage. Got it? And then actually the previous year questions actually I'll just go through it and you can see what kind of models are expected in this. Right, so this is in 2018. This is in 2021. Right? Two rods LM and MN are joined rigidly at the point M such that LM square plus MN square equal to LM square, and they are hanged freely in equilibrium from a fixed point L. Let omega be the weight per unit length of both the rods, which are uniform. Determine the angle which the rod LM makes with the vertical direction in terms of length of the rod. So this actually So equilibrium of forces actually under that particular category, we will have to solve this particular one. The second one is a heavy string which is not uniformly density is hung up from 2 points, let T1, T2, T3 be the tensions at the intermediate points A, B, C of the catenary respectively, where its inclinations to the horizontal are in arithmetic progression with common difference of beta. Let omega 1 and omega 2 be the weights of the parts A, B and B, C of the string respectively. Prove that harmonic mean of T1 and T2 and T3 are 3 T2 by 1 plus 2 cos beta. T1 by T3 equal to omega 1 by omega 2. And this is a problem statement, but usually actually, so this portion if you notice, a heavy string which is not of uniform density. Usually, till 2020, I have noticed the problem with uniform density. But in 2021, for the first time, actually, they asked non-uniform density. So this actually we have to keep it in mind, right? But other than that, actually, this is a straightforward question only. And you can find out the questions actually in the textbook itself. A heavy particle hangs by an inextensible string of length A from a fixed point and is then projected horizontally with a velocity of square root of 2gh. If IA by 2 is greater than h greater than A, then prove that the circular motion ceases when the particle has reached the height of 1 by 3 A plus 2h from the point of projection. Also prove that the greatest height ever reached by the particle above the point of projection is 4A minus h into A plus 2h whole square by 27A square. But this kind of models actually we will solve it in the class, but this problem as it is I didn't find in the textbook. Right? Describe the motion and path of the particle of mass m which is projected in a vertical plane through a point of projection with velocity u and a direction making an angle theta with the horizontal direction. Further, if particles are projected from that point in the same vertical plane with velocity of square root of 4 times of square root of g, then determine the locus of vertices of their paths, right? So this is a planar motion, right? Planar motion meaning it is in two-dimensional plane. If a planet which revolves around the sun in a circular orbit is suddenly stopped in its orbit, then find the time in which it would fall into the sun. Also find the rotation of its falling time to the period of revolution of the planet. So this is actually the planetary motion or the central forces concept. Actually, we will have to use it to find out this one, right? And so, but actually in 2021, I feel that the paper is a bit tougher only. It's not that easy. And this is in 2020, a uniform rod. And here actually, if you notice the questions that you can notice that, so this is a statics question. And this is also a statics question, second question also. And third question is a dynamics question. And the fourth question is a dynamics question. And the fifth question is a dynamics question. So 3 dynamics questions and 1 statics question. And 2020, right, a 4-wheeled railway truck has a total mass m. The mass and radius of gyration of each pair of wheels and axle are m and k respectively, and the gyration of each wheel is r. Prove that if the truck is propelled along a level track by a force p, the acceleration is p by m plus 2mk square divided by r square, and find the horizontal force exerted on each axle by the truck. The axial friction and wind resistance are to be neglected. So this is actually the dynamics question, and that is coming under the system of particles topic. And here a particle starts at a great distance with velocity v. Let p be the length of the perpendicular from the center of a star on the tangent to the initial path of the particle. Show that the least distance of the particle from the center of the star is lambda, where v square lambda is equal to square root of mu square plus p square v power 4 minus mu, where mu is a constant. So this actually, that is the central forces topic. So from that particular topic, this question was asked. And this is a square framework formed of uniform heavy rods of equal weight W jointed together is hung up by one corner, and the shape of the square is preserved by a light rod along the horizontal diagonal. Find the thrust of the light rod. So this is a straightforward textbook question. This is under the principle of virtual work. and a beam AD rests on two supports B and C, where AB is equal to BC is equal to CD, it is found that the beam will tilt when a weight of P kc is hung from A, or when a weight of Q kc is hung from D. Find the weight of the beam. Right. So this is also a statics question. And a light rigid rod ABC has three particles each of mass m attached to it at A, B, and C. The rod is struck by a blow P at right angles to it at a point distant from A equal to BC. Prove that the kinetic energy setup is 1 by 2 P square by M, A square minus AB plus B square divided by A square plus AB plus B square, where AB is equal to small a and BC is equal to small b. So I think this is a textbook question. And a uniform rod in vertical position can turn freely about one of its ends and is pulled aside from the vertical by a horizontal force acting at the other end of the rod and equal to half of its weight. At what inclination the vertical rod will rest? So this question also actually a textbook question. Got it? So these are the kind of questions I think that you can expect. And so based on this, actually you have to plan the difficulty of the questions. Got it? And so this is about the previous year questions. And then actually, yeah. So I have covered what is the syllabus, and I have covered what is the weightage and what are the books actually. So this is the important portions and the approximate number of hours actually I'll take around. So this is 35 hours I take it. Both statics and dynamics together, 35 hours actually I'll try to take it. And then actually this one, what are the books actually? Those are only books that are available in statics and dynamics. That is the Krishna series. Right? Krishna's statics, dynamics. But there are many variations of this, but whatever the books I follow, that I will show it to you, that you can take it. So this is actually the statics book. This is what I follow. This is a Krishna series statics book. And another book is dynamics. So this is the book actually I follow, dynamics. This is also a Krishna series book. Got it? And these books actually I follow, and I will solve the examples only from these books. Got it? And our material covers almost actually most of the aspects of that. Fine. So any questions on the analysis? Difficulty level. See, you can see that actually understanding the topic, interpreting the concept actually is not that difficult. That is straightforward and easier. But the questions can be twisted in any direction. So that difficulty is there. But conceptually, I can explain you, understand each and everything actually very, very clearly. You will be able to understand. Don't worry about it. But only thing is you need to practice more and more questions because the variations can be infinite. So that's why actually try to solve more number of examples from the textbook based on the concept, whatever I give it, because each model actually will give a different kind of difficulty. Understood? Concepts and understanding is easier only. Any other questions? Quite difficult to manage with GS, right? See this. So mains time frame actually you target more this. So that is whenever you plan for the examination, right? So you have to plan for 1 year dedicatedly. And usually actually we start with the mains and optional subject. That is actually this June actually we start with optional subject. And this entire December until December actually we will have to plan only the optional subject. Then actually in the next year actually before the prelims examination, right? So from January onwards, most focus on the GS part. And again actually you have to revise after the prelims examination the same mains part again, right? So that way actually you have to plan. And by the time you go to the exam, you have to revise at least 3 times. So that is how you need to be planning. And the first time actually it takes more time, don't worry. But in the second time actually it will be usually half of the time what you have taken in the first one. And the third one actually it hardly take actually 1 to 2 months maximum. Right? So that is how you have to plan. Understood? And if you wanted to parallel go with GS, then actually you have to spend full time and dedicatedly 4 hours you spend for the optional subject, remaining time you can spend for the GS. Understood? Okay. So yeah. So that's all for today. Yeah. Thank you.